Mr. Munyon here again with activity 14-1. We're starting points of concurrency here. Alright, so our goal is to determine a point of concurrency of altitudes of a triangle. Hopefully we have an idea of what altitudes are. We learned what an altitude is when we first figured out how to do area of a triangle. And then use point of concurrency of altitudes of a triangle to solve problems. Alright, so before we even get started, let's just make sure we remember what an altitude of a triangle is. There we go. Whenever you have a triangle, we think of altitude as the height. Oops, that wasn't that great. It just has to be perpendicular to a side of the triangle and go through the opposite vertex. So that could be an altitude there, or maybe this looks like maybe it's a right angle. Notice this side could be an altitude of the triangle because it's perpendicular one side and goes through this vertex. So ultimately you have three sides of a triangle. You could have three different altitudes on a triangle. All right. So the problem we're dealing with is actually going to be going for this entire lesson. Lucky Leon was an old gold miner whose hobby was mathematics. In his will, Leon left a parcel of land to be used as a nature preserve. The will included a map and the following clue to help find buried treasure. So at the point on the map where two altitudes cross, in a hole in the ground, some treasure was tossed. Stand at place where two medians meet, and the rest of the treasure will be under your feet. Each locked in a chest where they will stay until the time someone finds a way to open each lock with a combination using digits of the coordinates of each location. Okay, so looks like we need to find some altitudes, medians, and some coordinates here for where these places meet at. So if you don't know what a median is, we'll get to that lesson in a minute, but we're going to focus on altitudes. So we can see a little diagram of the parcel of land that was donated. Here we have some rivers and a lake running around Lucky's land right here, and it's kind of shaped like a triangle. In order to preserve the natural surroundings, with as few structures as possible, they decide on a nature design so that the visitor center will be at the vertices of this triangle. So we'll have a visitor center here, here, here. And a power station that is equidistant from the three visitor centers. So somewhere around here, wherever we can find a spot that's going to be equal distance from all three of these vertices. I don't know exactly where that's at, but equidistance just means it's going to be the same distance from all three of those. And a campground that's going to be equidistance from the shoreline. So somewhere around here, we're going to try and find a place that's an equal distance to the river here, the river here, and the river here. Not quite going to be the same point as the one that was an equidistance from the vertices. All right, so those are our goals here for the land. Get some visitor centers, a power station, and a campground on the land. All right. So the people, Al, Jeff, and Cal, decide that their first priority is to find the treasure. So they want to find where the altitudes cross to be able to figure out where some treasure was tossed, because maybe that treasure will help fund some of their plans. So since they do not know which two altitudes Leon meant, Jeff decides to place a grid over the map and draw three altitudes to find the coordinates of any points of intersection. So here is that Lucky's land where they put vertices, where the visitor centers are going to go on the corners of that triangular shaped island. First thing, determine the slopes of the three sides. So this is part of the process of finding the altitudes. So let's go ahead and do that. All right, slope of, let's go with AC. So it has a rise of 24, a run of 12, and that simplifies to 2. The slope of CG, so from C to G, has a rise of negative 24, run of 24. From 12 to 36, it goes over 24 units. So negative 24 over 24 has a slope of -1. And the slope of AG, that one's going to be easy. AG has a rise of 0, run of 36. All right, so the slope of AG is just going to be 0 over 36, or 0. All right. Now that we have determined these slopes, remember that perpendicular lines have slopes that are opposite reciprocals. So if we're trying to draw the altitude of one of these sides right here, going to the opposite vertex, I need to be able to draw a line that's perpendicular and goes through the opposite slope. So something perpendicular here goes through the opposite, something perpendicular here goes through the opposite vertex here. So we need to figure out what the slopes are, and then we can use those slopes from the opposite vertex to draw those. So let's go ahead and do that. What is the slope of the altitude from A to C to G? So what is the slope of this one right here going to be? Well, all I need to do is take the slope of CG, find the opposite reciprocal, and I'll have the slope that goes from A to CG. So let's go ahead and do that. Let me erase the dotted line I drew here so we can find the actual one. So a slope perpendicular to CG. Oops. So I just need to take this one and do the opposite reciprocal. So the opposite reciprocal of negative 1 over 1. The opposite sign is now positive. And the reciprocal of 1 over 1 is 1 over 1, or 1. Okay, so the altitude slope, 1. What is the slope of the altitude from C to AG? So if I figure out AG has a slope of 0, the opposite reciprocal is undefined. Perpendicular to horizontal would be a vertical undefined line. The last one, slope perpendicular to AC. We take AC and do the opposite reciprocal. So the opposite reciprocal of 2 equals negative 1/2. So the altitude is going to have a slope of negative 1/2. Should have put that one on there. M equals undefined. So our altitudes are going to have a slope of positive 1, undefined, and negative 1/2. So now that we know those slopes, use the vertex with its corresponding altitude to graph each of the 3 altitudes. Okay, so let's start with the easy one. I know that opposite of AG is vertex C, and instead of using a slope of 0, I need to go through this vertex and have a slope that's undefined. So I'm just going to draw a line here. Should be a nice vertical line, and it should be perpendicular there. For CG had a slope of negative 1. The perpendicular line would have a slope of positive 1. So from this vertex, I need to have a slope of positive 1. Instead of putting on each of these 2, 2, 4, 4, 6, 6, 8, 8, 10, I'm just going to use these points here to help me draw, and then connect that line. All right, so the last one here had a slope of 2, so the opposite reciprocal should be 1/2. So rise of 1, run of negative 2. Not perfect, but something interesting happens. Notice right here, it looks as though all 3 of these altitudes happen to intersect at the exact same place. Which is what the next thing says. After drawing these, Jeff is surprised to see that all 3 altitudes meet at exactly one point of concurrency. The point of concurrency means that the lines are concurrent at that one point. They all go through that one point. All right, state the coordinates of that point of concurrency. So it looks like that was at 2, 4, 6, 8, 10, 12. 2, 4, 6, 8, 10, 12. So positive 12, positive 12 is what we ended up coming up with on that one. All right, so Al is not convinced that the altitudes are concurrent. Maybe we drew it, just happened to be, looks like they're congruent. So he wants to use algebra now to determine for sure. So use algebra to find the point where the altitudes meet. Basically, we're going to solve a system of equations. We're going to see if we can't come up with an equation to represent the altitudes. which we should do. We can write an equation using a point and a slope, or a couple of points, whatever it is that we need. We can do it in slope-intercept form or point-slope form. And once we have those equations, we can solve a system of equations and see where they intersect at. Find the one point that's on both of those. So state the coordinates of one point on the altitude from A to CG. So from A to CG, 0, 0 would be an easy one that we could use for that. Okay, write an equation of the altitude from A to CG, and we can put this in point-slope form. So y minus y1 would be a coordinate from here, equals the slope. So remember that slope should have a slope of positive 1 because the perpendicular line had a slope of negative 1, so the slope will just be positive 1. X minus x1, and we can just plug in the x coordinate there. So simplifying, we get y equals x. That doesn't need to be there. You get x minus 0, so just x. 1 times x is just x. So we get y equals x. And that makes sense because if you think about it in slope-intercept form, the slope is 1, the y-intercept equals 0. So far, so good. Write the equation of the altitude from C to AG. All right, this one should be easy as well, from C to AG. This one is a vertical line which will be represented with x equals, and x equals 12 because it crosses the x-axis at 12. This is not a function, so we can't write it in y equals. So x equals 12 is going to be this one. Remember, there is a little reminder here about vertical and horizontal equations. All right, and write the equation of the altitude from G to AC. So we just need a point that we can use and the slope, and we can plug in point slope form. So from G here, there's definitely a point at 36, 0, and the slope was negative 1/2 that we came up with. So to AC, yeah, it should have been negative 1/2. So we'll use 36, 0, and the slope was negative 1/2. So G was at 36, 0, and the slope we're going to use equals negative 1/2. Whoops. So y minus y1 equals m x minus x1. Let's plug in our pieces. And we get the equation here. If you want to leave it in point-slope form, you're welcome to do that. If you want to put it into slope-intercept form, be real easy to just get rid of the 0 here because you don't need it, and then distribute the 1/2. So we could also write it in slope-intercept form. We get y equals negative 1/2 x plus 18. When you distribute here, you get negative 1/2 x. A negative distributed to a negative 36, you get positive 18. So the slope is negative 1/2, y-intercept is at 18. Just checking to make sure. It looks accurate. It looks like the y-intercept would probably be around 18 if I extended it over there, and it does have a negative slope. Okay, so we got our 3 equations. Great. Looks like we have an equation here, here, and here. Now that we have these equations, we can find a point of intersection by solving the system of equations. So altitude from point A and the altitude from point C, let's start with that one. That should be the easiest one. So this first equation and the second equation, let's use those two. Okay, so the 2 equations are y equals x and x equals 12. This is going to be a real easy substitution. If x equals 12, you just plug it in. So y equals 12. And your solution set is x equals 12 and y equals 12. So the point of intersection of those 2 lines is going to be at 12, 12, exactly what we got. What about verify the point of intersection from item 6 on the altitude from point G? So let's check and see if this solution set also works in this equation. We can just see if this point is on the line, because if it is, it goes through that point. Obviously, it goes through there. So we could plug in y equals negative 1/2 x plus 18. This is the equation of the line from G over this direction, and we're going to see if it goes through the point 12, 12. We're going to plug in 12, 12 and see if it's a solution set, see if that point is on the line. All right, so my Y value I can plug in is 12. My X value I can plug in is 12. One half of 12 is negative 1/2 of 12 is negative 6. And negative 6 plus 18 is 12. So this is a solution set, which means the point 12, 12 is on there. So all three of these altitudes that we created do go through the point 12, 12. Explain why, number 8, explain why algebra from items 6 and 7 demonstrate that the three altitudes are concurrent. Because 12, 12 is a solution to all three. So that point is concurrent on all three lines. So it is concurrent on there. All right. Okay. Al reviews the first clue and says at the point on this map where the altitudes cross and a hole in the ground, the treasure was tossed. So apparently we've identified it. However, he's also not convinced that altitudes are concurrent for every triangle. Maybe some other types of triangles, they cross at different points. So it says use some geometry software. Let's go ahead and do that and move some vertices around and see if it stays concurrent. So here I have set up the three vertices at 0, 0, 12, 24 for point B, and 36, 0. And if I was to draw some perpendicular lines from each of these vertices to the opposite side, let's go ahead and do that. Where's perpendicular at? Perpendicular line, so select a point and then perpendicular to do that. So point and perpendicular line here. Point and perpendicular line. This is the GeoGebra. It's in the extra resources on the website if you wanted to do this as well. It's a fun little resource. I do see they are definitely concurrent here, and it's at the coordinate 12, 12. So 10, 12, 11, 12. Oh, these are counting by ones here, so 10, 11, 12. Yep. All right, let's see if I can move some of these around, drag it around, and if it still stays concurrent. Yep, no matter where I put this, we can literally see that all three altitudes are always going to meet at the same point. That is actually kind of fun to do. I don't even remember where this was at. 12 and 24. If I move this one around, we still see that they always meet at the same point. All right, so back to our lesson. Do the altitudes remain concurrent? Yes, no matter where you move the vertices. Is the point of concurrency always inside the triangle? No, we noticed a few times that it was not always inside of the triangle. Like if I was to move this, as soon as I make angle B, notice as soon as it's an acute angle right now, if I make it a close to a right angle here, oops, I guess this is more of a right angle here. It's on the vertex, but as soon as I make it an obtuse triangle, so B is an obtuse angle, the point of concurrency is outside of the triangle. Same thing here. If I make C an obtuse angle, the point of concurrency moves outside of the triangle. All right. So the first part of the buried treasure was located at the orthocenter. This is the name of the point of concurrency of three altitudes. This is an important vocabulary word. You need to know what an altitude is, and on a triangle, three altitudes meet at an orthocenter. What are the coordinates we came up with? 12, 12. All right. Explain why two of the altitudes of a right triangle are its legs, because on a right triangle, two of the altitudes are its legs because this vertex here, perpendicular to the opposite side, is the leg. So two legs are already a line connecting a vertex perpendicular to an opposite side. So explain why two altitudes of a right triangle are its legs. The legs are perpendicular to, each leg is perpendicular to a side and goes through the opposite vertex. All right. If one altitude of a triangle lies on the triangle's exterior and one lies on the triangle's interior, what is true about the location of the third altitude? Well, the third altitude would have to be on the exterior because if one is on the exterior, that means you'd have to extend one of these sides out past the obtuse angle to be able to create a right angle that still goes through the vertex. So the last altitude needs to be on the exterior angle. And let's visually look at that a little bit more with this here. Notice here, as soon as I make C an obtuse angle, two of the altitudes here are on the exterior, one's on the interior. Same thing here. If I make B, two of them are on the exterior and one of them is on the interior, but you have to extend it past out as well. So this is never on the inside of the triangle. This is never on the inside. This is on the inside, but to find out the point of concurrency, it does keep going past point B about here as well. All right. So we have some lesson practice. Graph the altitudes and the orthocenter of this triangle. And number 14 through 18, what I'd like you guys to do is I'm only going to go over the two graph ones and one of these two, but I'll put the answer for the orthocenter down for 16, 17, 18, just so you can check your work. Pause here, work on 13 through 18, restart your video when you're ready to check your work. All right, I hope that went okay. This first example here did happen to be a little bit tricky because you don't get nice whole numbers, but let's go ahead and check it out. So let's start with BC, has a slope rise of 5, run of 4. So if the slope of A is positive 5/4, that means the altitude is going to have a slope of negative 4/5. So from A, if I go down 4 over 5, I will get a point there that I can connect. So let's go ahead and do that. Okay, does have the correct slope there. So what about AB? So for line C right here, that has a slope of negative 6 over 3. So negative 6/3 simplified is negative 2. So that means the opposite reciprocal, or the altitude, should be going through positive 1/2. So from here, if I use a slope of positive rise of 1, run of 2, or go the other way, negative 1, negative 2, I should get this line right here. Okay, so we already can see the point of concurrency does not look like it's going to be on a nice whole number. And I shouldn't actually need to do the third one here to be able to check, because I know for sure it's going to go through that point. But I'll go ahead and draw it here. This has a slope rise of negative 1, run of 7. 1, 2, 3, 4, 5, 6, 7. So negative 1/7 would be a positive 7 over 1. So if I go up 7 here and over 1, should be right around here. So let's go ahead and connect those as well. So this looks at, I went ahead and added the slopes as well. It looks like we're going to get a really ugly fraction point of concurrency. So let's go ahead and set up two of these, whichever ones we think. I'm going to go ahead and use this one here because it's a whole number, and this fraction 1/2 should be the easiest ones to use. So I'm going to use this point and this slope to write an equation. So that's the point 9, 5. Oops, there we go, 9, 5 is my point, and the slope I'll be using is 1/2 to write an equation. And I'll go ahead and put this into slope-intercept form just to make it a little bit easier. I'll go ahead and distribute and then combine my like terms. 0.5 or 1/2, doesn't matter. Negative 4.5 plus 5 is positive 1/2 or positive 0.5. For the other equation, I mentioned I was going to use this one here, so I can use the slope the point 50 and the slope of 7. So the point 50 and slope of 7. So y minus y1 equals mx minus x1. And this one should be a pretty easy one to simplify here. Y equals 7x minus 35. And that does look like the y-intercept will be pretty far down there at like negative 35. So now that I have my two equations here, I can solve using a system of equations using substitution. And this is definitely the easiest way to do this because now I can, since I know what y equals, I can substitute this in for y. Basically, just set the two equations equal to each other and solve for x. So 7x minus 35 equals 1/2 x plus 1/2. So subtract 1/2 x from both sides. So add 35 to both sides. Let's say we wrote it as a fraction, 13 halves x equals 71 halves. Dividing both sides by 13 halves, dividing by a fraction is the same thing as multiplying by its reciprocal. So you get x equals 71/13 as a improper fraction. If you write it as a mixed number, that's going to be 5 6/13. So 5 6/13. For our x value, that does look right. So 5 6/13, not quite. Well, 6/13 is not quite half of another unit right there. So our x coordinate does look accurate. Once we know x, we can plug it in and solve for y in either of our two equations. So if x is 71/13, I can plug it back into either one. So let's take which one would be the easier equation? Well, let's just plug it in the bottom one. I plugged it into this equation here. So x is 71/13. Oh man, this is really ugly. 7 times 7 is 497. Minus 35. All right. Looks like a calculator would be helpful because I'm not going to try and figure that one out without my calculator right now. Or I guess we could just find common denominators. So y equals 497/13 minus 35 times 13 would be 455/13. So it looks like we get 42/13. So that should be 3 3/13. Because 3 would be 39, and you've got 3 more. So 3 3/13 is your y value. So 1, 2, 3 3/13 up. There we go. That is really ugly. So 71/13 and 42/13 would be your coordinate on that one. Man, that one was really ugly. I would suggest if you have the GeoGebra, or if you just go to the GeoGebra website, to just do it on there. So like 2650, I would just go there and create one like we did here and do the altitude. So 26. I don't remember what the other ones were. So 9 and 5 is the last point, and the altitudes meet at the ortho center here. We do get the same thing, 5 and well, I don't remember what it was, 6 or 7 13, so a little bit less than 5.5, and then 3 and 3/13. Yep, looks like about the same thing for the x and y coordinates. Is there a way to figure out this one? Oh wait, it's down here as a decimal. Guess it won't give you the fractional answer. If you had a test, you could convert your fraction to a decimal and see if it was the same thing. All right. All right, on this problem, I like it because picking up where we left off now on question 14, this is an obtuse triangle, which means we are going to have altitudes that are outside of the triangle, and the orthocenter should meet out there as well. I do want to point out that the altitudes need to be perpendicular to a segment and go through the opposite vertex. What is opposite of BC? A is the vertex that's opposite. So it needs to be perpendicular and go through A. The only way it can be perpendicular and go through A is if it's way over here. So I've already written down the slope of BC. So it has a rise of -3, run of 5. The opposite reciprocal would end up being positive 5/3. So a rise of 5, run of 3. I don't need to go that way here. I can't put one anyways, but rise of -5, run of -3. This is still a positive slope. We get these here, so let's go ahead and graph that one. Okay, same thing with, let's do an easy one here. AC looks like it goes from 7 down to -2, so a rise of -7. Or from -3 to +4, 7. So this actually has a slope of -7/7 or -1. So the perpendicular slope is then just going to equal +1. So I need a +1 slope that goes through here. This one's going to be a pretty easy one to figure out. Let's go ahead and graph that. It should be going through all of these slope of +1 points. Let's go ahead and graph that too. All right, so we got that one. I guess maybe to add something to the picture here, I can show that, whoops, my bad. I can show that this side was extended here, so -3/5. So. And that way I can see that the line we drew here for the altitude is perpendicular to BC. You'd have to extend an imaginary line out for BC, but it is perpendicular to it, even if it doesn't touch it. And we could do the last one if you really wanted to, but I see that 2 of them are already going to meet somewhere way down here. And I don't know what that point is. So we could do the system of equations now, because this other equation isn't going to be any easier. This has a slope of net from 5 to 1, so 4 and 2. The line there, AB, has a slope -4, 2, so -2. The perpendicular would be +1/2. I guess that's not going to be too bad. So +1/2 should be here, 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 here. We actually could find this one pretty easily because that's definitely going to be on a nice whole number there. And these are all on whole numbers. So your answer has to be a whole number because all of these are nice whole numbers. I guess it could intersect somewhere in between. Oh, well, I would suggest you could use your coordinates and your slopes if you wanted to. Or you could use the GeoGebra software. I would definitely recommend using GeoGebra. If you've got it, just because it's good practice and a little bit faster. If you want to set up your equations, you can do that as well. I'm going to set up the equations here, and I'll pause the video and just have the answer to the equations up here in just a second. All right, so here is point A and the slope of the altitude that goes through A, and write it in point slope form. Y minus y1 equals m. X minus x1 minus a -3 is the same thing as +3. Simplify and put into slope-intercept form, so that makes solving them later a little bit easier. Same thing, here's the coordinate for B, is at -1, 1. The slope that goes through B has a slope of +1. slope-intercept form, y minus y1 equals mx minus x1 minus a negative 1 is the same thing as plus 1. Add 1 to both sides, and we get the other equation. Now that I have my two equations, I can use substitution to solve, and since I know what y equals, I can substitute in for y. So I substituted in, instead of y, I put x plus 2 equals the other equation, 5/3 x plus 10. Solving, we end up getting x equals negative 12. Once you know that x equals negative 12, you can plug it in here. Negative 12 plus 2 is negative 10. So my coordinate when I'm done, finally done with everything, the orthocenter is going to be located at negative 10, 12. All right. Down at the bottom, I'm just going to put the answers down there. You can check your work. So here are the answers for 15 through 18. Most of these actually weren't too challenging because you did get nice whole numbers for your solution. You didn't have to deal with any ugly fractions. Some of the equations, not too bad. Notice there were, a decent number of zeros here, which actually makes some of the algebra a little bit easier. And even 18 had a 0, 0 coordinate, which is kind of convenient. Remember, you only have to find two of the altitude's equations to be able to set up a system. And you might want to try and make sure that you're using, if there's a nice vertical or horizontal line, those are one of the easier ones to use. All right, well, good luck, because next we're going to be learning about medians, and we're going to be doing the same thing with these. Finding points on medians, writing equations, find where they intersect at. So I will see you for 14-2 over medians and their point of concurrency centroid.